Welcome to today's seminar series. We are very fortunate and we're extremely excited to have our speaker today all the way from the University of Toronto. He is a professor and Clarice Chalmers Chair in Engineering Design in the Department of Mechanical and Industrial Engineering at the University of Toronto. His research is concerned with human interaction with automation and safety and mission critical operations in the process industries and military applications. Ladies and gentlemen, help me welcome Dr. Greg Jamieson.
Well, thank you very much for the introduction there, and hello to everyone. I have been waiting for you for an hour because I forgot that Oklahoma is on Central Time,
Oh,
so I wasn't careful enough in planning my day. So I've been anticipating this for at least an hour longer than you, but I am looking forward to having a chance to speak with you and share some of the recent research that we've been doing and in fact are just wrapping up. I'm going to try to share my screen and I'm looking to see if I share presenter view. I'm concerned that you will see. Do you see now the next slide as well?
yes, you can see that.
You can see the next slide. So you're not just seeing the presentation. So
I mean, I
I'm
see
gonna,
both slides.
yeah, you see both, but it would be certainly a lot nicer if I could show you just the one. I'm not quite sure why, if anyone has any suggestions, because when I go and look in my sharing, I don't see the opportunity to share just the one slide. Okay. Well, perhaps I will instead, bear with me for just a second. Perhaps
Okay.
I'll switch out of presenter view and just do it in the regular everyday view. And I'm switching back. Now we'll try this one more time. There we go. All right, does that look a bit better?
Yep, it does. Thanks.
All right, very good, very good. So, thank you again. It's a pleasure to join you today. Um, I'm Greg Jamieson, as the introduction suggested, and today I'm going to be talking about some of the research that we've been doing with augmented and reality navigation, and which we've been testing largely in the virtual reality space, which I'll discuss in the talk. Like any academic activity, of course, I'm sure you're all familiar with this. This is a collaboration with other investigators. Paul Milgram, who, if any of you do any sort of augmented, virtual, or mixed reality work, you'll recognize his name from his taxonomy of augmented reality. Justin Hollins, who, if you're in the human factors space, you'll recognize that name as the co-author with Chris Wickens on the engineering psychology textbook that is pretty much used in every human factors program that I'm aware of. And then Tom Kapler, who is the partner at Uncharted Software, who arranged for funding of the work and is the originator of the design idea that we were testing through the work. But most importantly, as you know, the graduate students do all the heavy lifting, do all the work. So the work I'm going to be presenting today reflects primarily the work of two of our graduate students, Holland Vasquez, who completed her PhD late last year, and Adam Reiner, who will complete his work early this year. So we're at the end of this long, okay, now how can I advance my slides? There we go. We're at the end of this, it's been a 4-year research program, and it was instigated by an intersection between a need from the Canadian military, which is really reflective of needs across many Western militaries, intersecting with a technology concept that the industry partner Uncharted Software had developed. So the need on the military side is to enable soldiers, particularly what are referred to as dismounted soldiers, so they're soldiers moving on foot and not in vehicles, to navigate urban environments. And these environments are particularly challenging, especially for North American militaries that have been their doctrine is set by the idea of maneuverability, the idea that you'll have lots of space and you want to move your forces in that space to multiply the force advantages. And in urban environments, it's very difficult to do that. The terrain is essentially very dense. You have a lot of these objects that you can't move through, and that put civilians and other neutrals in close proximity to combat forces. You end up in that environment with a dispersion of friendly forces, so you have units that are spread out and have difficulty coordinating with one another. And consequently, and this has been seen in the US military's experience in Iraq, the Russian military's experience in Chechnya, this is, and also several different militaries' experience in Syria, that these settings result in a very high increase in casualties. So they're very dangerous environments for military operations to take place in. And there's been a recognition for some time that augmented reality may offer support for soldiers in this navigation task. There's been an increasing prevalence of technologies, body-worn technologies, that are aiming to assist soldiers. But one of the challenges for these things is that current displays for navigation have been limited to providing pretty much exclusively route or landmark information. So essentially, as a viewer is looking out in the real environment, we use the augmented reality to paint information about the destination or the path to the destination, or sometimes at landmarks, so particular items or places in the environment where people will want to sort of recognize some point that they're going to turn at or move away from, these types of things. And what is actually really valuable to soldiers and to other navigators from a map is the survey information. So this is the relational information that's contained in a traditional map. And it's quite difficult to convey that in augmented reality. And so there are several reasons that we were interested in this technology that Uncharted Software had developed and patented, which was the idea of what was called a SkyMap, which was to use the space that is above the head of the navigator to present survey-related information at a very large scale and in alignment with the user's track-up direction. And so that's the technology intersection with the problem that we were exploring in this research. And so SkyMap, and you might be shocked at how long it took us, many months to come up with a one-sentence description about what SkyMap is. But what it is, and I'm going to show you sort of how we construct this to give you a solid understanding of what SkyMap is like. But it's a world-aligned bird's eye view map whose reflection is viewed on a simulated mirror-like surface positioned above the viewer. So what you can kind of imagine is if you're moving through the world where the entire sky is a mirror that is reflecting a map that effectively you're moving through while you're still able to view what's in the environment around you. And as you might imagine, this begs a ton of questions about, well, what is the shape of that mirror? What information is available on that mirror? And how do humans perform when trying to make use of information, that survey information that's contained on that mirror? And so we can sort of help you to envision how SkyMap works through this graphic. So first of all, imagine that you're navigating through an environment and you have a map, right? And that sort of light green is the shape of your map, and it represents a scaled version of the world, right? So it's scaled down, and we know that there's a lot of research on the impact of map scale. So we know that scaling down a map makes it more challenging to use because it requires a frame of reference transformation by the user to essentially expand the map to the world or contract the world to the map. If we could then actually create a map that's as large as the world, we wouldn't have to deal with that problem anymore, that problem of scaling. And we can potentially do that by essentially turning the sky into a map. So we can increase that scale. And then what we can do is project information, survey information from the surface up to that map and reflect that information back down. Now, this flat map projection is quite ideal because you don't have problems with compression or expansion of any of the elements that are on the surface. But essentially, the real challenge here is that now to understand one's own position, you essentially have to look straight up and crane your neck, look straight up. And so that didn't seem like a very good idea. So the next idea was to sort of bend that map and turn it into a dome. And by bending that map around, then things that are at a distance are more easily viewed because they're not quite as far away on the, they're not perceived as being as far away on the map. Of course, this then creates a problem of essentially distorting the representation that's presented on the dome is a distortion of what's in the world. And we know that those distortions will have an impact on human performance. And so we need to learn about that. But then the other thing that we want to do is make it easier, especially when a navigator is moving, when they're wayfinding through the environment, to be able to see their own position. And so early prototypes for SkyMap wanted to move the position of the own representation, the own avatar representation forward in the field of view so that it would be easier for the user to see themselves and where they were headed through the environment. And of course, that creates problems with compression and expansion in the map. But of course, now bear in mind, this is a two-dimensional representation, and SkyMap is a three-dimensional concept. So it's not just an arc, it's an actual dome. So that as the user turns his or her head, the map is then moving and turning with them, right? So it is that full, like if you turn around and look behind you, everything behind you is not expanded. It's compacted just like it is in front of you. Just as you turn around, that representation has to be rendered for you. Okay, so we knew we wanted to do some human performance evaluation with SkyMap, but we also learned very quickly that AR displays have a quite limited capability. And this is, of course, also now 5 years ago when we planned this research, that the AR display capabilities were even more limited than they are now. We have built an AR version of SkyMap. Really, I should say that Uncharted Software has built the AR version of SkyMap. And you essentially have two choices. You can either put it in a vehicle, which is exactly not what the Canadian forces were interested in us learning about, or you can put it on like a big cart and you can push it around with the person wearing the goggles, because the computing power that you need, you kind of have to move a trolley along behind the person. So this clearly was not going to work from a human factors research program perspective. The other thing is that in order to study the effects of these different map manipulations on the navigation performance and the workload experience of the users, we needed to have greater experimental control than we were going to be able to get out of an augmented reality environment. And then the last thing, of course, is safety of participants. We were not very excited about the idea of going to our research ethics board and saying we were going to put these goggles on people and have them walk around a physical environment where they could trip over things and run into things. And so safety was a major concern. And so for that reason, what we decided to do was to start a research program in VR instead of in AR, so that we could test these concepts and decide over time whether or not it was worth waiting for this technology, the AR technology, to mature to the point where we could deploy it there. And so we then went about creating this virtual environment in Unity, and that looks something like this. It allows us to take a virtual version of a real environment, and we were using environments that we were able to get. This is the environment that we selected was in Brixton in the UK. The reason for that is we were looking for an environment that did not have, say, orthogonal roads, because we wanted more challenging navigation environment. And we also wanted an environment where the buildings were not too tall, because there are challenges to creating or painting this map on the sky or overlaying it on top of buildings if you have to. And there's also some operational challenges that come around from that as well. So we were looking for a bit of a simplification. And so a non-orthogonally laid out city with relatively low buildings was ideal, and Brixton served our purposes. So the actual maps that we're using in the experiments that I'm going to show you are maps of a real environment. I think trying to remember the name of the application, but they are geographically aligned to the environment. And then finally, we needed to be able to represent these different types of maps in this virtual environment. And we obviously want to test the SkyMap concept, but we also needed to be able to contrast it against more traditional map formats. And so the way that we did this was through a version of SkyMap that the client referred to as Mirror in the Sky. And so Mirror in the Sky is the VR implementation of SkyMap, and it looks something like this. And then we can compare and contrast the different maps that we're interested in. So if you know anything about navigation, one of the key questions in designing for navigation, for the creation of maps, is whether or not the map will be north up or track up. And so there are advantages and disadvantages to both types of maps. They're well studied in the human factors literature. And we wanted to compare that to the MITS map. And so you can start to get a sense here of what the rendering looks like of the environment with the different maps. For the track up and the north up map, we're rendering this map as if it were available essentially right in front of the user, much like a paper map might be. And in the MITS case, that map is rendered overhead. And you can see how that works out. You can also see in the left image, you can see that we used outlines of buildings so that we could paint the map over more of the surface. That was obviously going to be a design challenge for using that overhead space. The other thing you see in this environment that you'll see referred to later are these obstacles. Essentially, the challenge that we learned in pilot testing is that some users would simply drive the self marker on the map. So they would just stare at the map and move and watch what happened to the self marker. And because they knew there was nothing else in the environment, there were no cars driving around, there were no people, no potholes. So what we had to do was create a set of obstacles and then tell people that they would essentially be penalized for running into to those obstacles. So some necessary manipulation, some fakey of the environment to make the tasks somewhat realistic. Okay, so we now have this virtual environment that's going to be presented through an Oculus Rift VR headset. That was powered by an Alienware laptop. And then we implemented what's known as either the detection response task or the discrimination response task. Essentially, if you look at the figure in this environment, you can see that there's a tactor placed on the right shoulder. There's another tactor placed on the left shoulder. And depending on whether or not you're using the detection task or the discrimination task, you either just use those tactors to tap on the shoulder and have the person tell you whether or not they detect that, or you can tap on both shoulders, either shoulder, and tell them only to respond to one or the other. And this is essentially what's known as a secondary workload task. So it's a secondary task because it's not the primary thing that they're doing, which is moving through the environment. But it's used very widely in driving research, and we adopted it here. And so you can see that there. And then we needed a laptop to control that. And then finally, as a physiological measure of workload in our studies, we had hooked everyone up to a Polar H10 HR monitor so that we could do physiological measurements of workload based on heart rate and heart rate variability. And so that's what that DRT data collection software, or sorry, data collection system looks like with the software generating these actuations of these on the shoulders, and then the respondent using the hand controllers that were available through the VR system to respond to those signals. Okay. So that's what the environment looks like, and that's what the testing apparatus looks like. Now the question is, or the question for the students was, what do we want to know about this? What do we know about human performance in navigation and wayfinding that we will want to investigate using this MITS simulation? And so these are some of the topics that we've looked at. Obviously, we're concerned about the performance of the wayfinding task itself, and then supporting that performance is all sorts of different notions of how the users are conceptualizing the space. So there's this spatial visualization, The spatial memory and spatial awareness are all facets of the research program that I'm not going to be talking about today. But instead, I'm going to talk primarily about the wayfinding task performance and the implications for workload. We've also done some research on thinking about what the cost of accessing the information in these different representations is, using a notion that's called information access cost that was developed by Christopher Wickens, which allows us to try to measure essentially the difficulty of the frame of reference transformations that the users have to go through with these different map representations. So I'm going to talk about 3 different experiments that we ran. Fortunately for you and for me together, I'm not going to go into a great deal of detail about each of these experiments, but enough to sort of show you what it is that we were evaluating and how people were performing and what we learned over the course of multiple studies. These are 3 of about 10 studies that we've run, so there's a fair bit more that I'm not going to talk about today. So if you're interested in other aspects of this, I'm certainly happy to receive questions about that or put you in touch with people who've done more of those experiments. So these experiments that we're looking at are going to look at the effect of map format. So whether we're talking about MITS, the track-up map, or the north-up map, and the effect of practice and the impact of those manipulations on mental workload and performance in the navigation task. So the first experiment looked at the effects of map format on performance and mental workload in what is known as a rerouting task with soldiers. And so in this task, we used Canadian Forces soldiers from a Quebec regiment known as the Vendu. And the Vendu soldiers were performing an exercise in Montreal. So we were able to take our equipment over there and work with them to collect some data, which was a lot of fun. And essentially what they had to do in the virtual environment was to look out for both cars and columns of smoke that might indicate threats to them, threats to their safety. And they were given a task of moving through an environment and avoiding those threats. They had other tasks that I'm not going to talk about here, but essentially they're trying not to get too close to something that could potentially harm them. Following a route that they were given. And of course, when they come across an object that they're not supposed to get too close to, they have to find a way of moving around that object in the environment without getting too close to it. Because they are military soldiers pretty much throughout the world are trained to use north-up maps almost exclusively. And MITS does not work that way. MITS is necessarily a track-up because it's world-aligned. It's a track-up map. So they were contrasting use of either the MITS or the north-up map in this case. And they did that DRT discrimination task for workload. They had to avoid those obstacles that I showed you a few slides ago. And at the end, they completed a bunch of questionnaires about their system acceptance and workload and other factors. So the dependent measures included their performance on the task, how quickly they moved through a map of a fixed length, a path of a fixed length, and how many times they ran into objects along the way. Their mental workload was assessed in 3 different ways, subjectively using the NASA TLX questionnaires, physiologically using HRV measures, heart rate and heart rate variability measures, and then finally through the secondary task performance on the DRT. And then finally, we asked them questions about their preference and system acceptance as well. So what did we think would happen? Well, essentially, we had believed up until the point we started doing experimentation with MITS that to the extent that it would be easier for people to be able to relate objects in the world to objects on the map and vice versa, that they would do better in navigation tasks and have lower mental workload in doing them. So that was our main hypothesis going into this line of experimentation. And as it turned out, as all good research stories turn out, we were dead wrong. So it actually turned out that these soldiers, when moving through these environments, when they were using the north-up map, so this is now a north-up map, maybe that's right down in front of them, they ran into fewer things, and they also got to the end of their paths sooner, and they perceived that north-up map to be more useful to them. Now, despite that, these clear differences in performance, there were no observed differences in workload across any of those 3 measures. And so we observed this dissociation between the task performance and the workload, which was a bit surprising to us. We expected those things to align more readily. So now the obvious sort of explanation that we had for this observation was that the soldiers have done a lot of prior training with Northup maps. So irrespective of the introduction of the virtual environment, they are trained to use Northup maps in operational environments. They're given Northup maps. They just use Northup maps. In fact, some soldiers told us that when they use like their GPS systems, they choose Northup maps in their GPS systems just because they find them more familiar. But MITS is clearly not that. So we thought that maybe that them performing better with the Northup map was an artifact of their experience. And of course, from the human performance literature with different types of maps, we know that track-up maps are preferable to Northup maps for a number of different types of tasks. And so we were really curious to know, okay, well now if we throw a track-up map in here, what are we going to see? So moving on to experiment 2, we then tried to address sort of both of those questions. We tried to address the map format question by then adding the track-up map into the mix, and also to address the user expertise by performing another experiment that included soldiers and then a group of civilians as well. And again, we were having them perform these navigation tasks and looking at their performance and their mental workload as well, again, across those 3 different measures of mental workload. So we expected, based on our experience from experiment 1, that we would see a main effect of user expertise, right? So we thought, again, soldiers having a lot of experience in using maps would do better than civilians, even though civilians very often, and just like you and me, have experience in using GPS systems and maps on our phones. We did think that soldiers with their training and experience would be more effective there. We also expected that there could be an interaction effect between the different categories of users and the map format. So, for example, we thought when soldiers were using the Northup map, they may show greater advantages than when they were using the track-up or MITS maps. And again, we did path following, but this time we did not introduce the threats in the environment. So took out the cars and the smoke columns. And that was largely because we were a little bit concerned about whether or not performance on some of the tasks that I didn't talk about by the soldiers was rather poor. And so we were concerned that civilians would have a floor effect on those tasks and not be able to perform them. So they're simply doing path following in this case. We give them a path on the map that they are using, and they have to follow that path through the environment. And so they were again using the MITS, the Northup or the track-up maps, had that secondary DRT discrimination task going on. Again, they have to avoid obstacles in the environment and complete some questionnaires for us at the end of each trial. And again, we were looking at their performance, their workload, and also their system acceptance. And so the results here showed that task performance was worse with the MITS display than either of the 2 conventional maps. And to the extent to which those differences were significant depended on which measure we were looking at. In the distance remaining, so this is this time, instead of a distance constrained task, we use a time constrained task. So how much of the potential route did they have left at the end of the trial? And you can see people in the MITS condition had more than in the track-up or the Northup map. That difference was significant comparing MITS and track-up. Whereas if we looked at the number of times that they ran into things, people using the MITS map were running into objects quite a bit more frequently, significantly more so than with either the Northup map or the track-up map. Now this time, mental workload actually showed as being higher with MITS than the more conventional map formats. Those differences were only significant between these are results from the DRT task, and they were only significant between MITS and the track-up maps, but you can see those differences there as well. And then finally, looking at the effects of the the expertise of the participants, soldiers generally performed better on the primary task, which is as we expected. They have more experience performing tasks like this. They're trained to perform tasks like this, and indeed they completed more of the path, and they had fewer collisions with objects in the environment. Now, the subjective mental workload was a bit more of a conundrum to figure out, this interaction. It did depend on both the user and the map format. As you can see, soldiers perform best when using that familiar Northup map format. There's basically no difference between the two groups in TrackUp, and civilians were a bit experienced higher workload with the MITS map. So you can see that there are some intersections there with the experience that participants had with navigation type tasks and the types of maps that they were presented with. So the results from both experiment 1 and experiment 2 suggest that people don't perform as well with MITS, and under certain circumstances they have higher mental workload when using this display compared with some conventional maps. And so what we really wanted to know is, to what extent was this related to the amount of practice that they had? So we had another experiment that I am not discussing here today, where a different student, Reiner, had showed that participants who were familiar with virtual reality, who had more exposure to virtual reality, had a better experience using the MITS system than others did. So we thought that practice, both sort of knowledge of the virtual environment and also exposure to the virtual environment, would influence the performance and the workload over time. And if that's the case, we were curious to know, well, how long would that attenuation take? Because if it's a long period of time, then that doesn't really help any proponent of MITS. If it's a short period of time, well, then that might be an acceptable cost to a display that otherwise provided other advantages. And so the final experiment that I'll talk about today, experiment 3, looked at the effects of map format and practice on performance and workload in this navigation task. And now we were only using civilians, because with civilians we could better control. I'm sorry, I'm going to have to excuse myself for a moment. My daughters have to have piano practice, and I need to help them for a moment. So please bear with me for just a second.
Okay, Greg.
Did you see the thing I printed out that was on the stairs? No. Okay, there was a piece of paper on the top of the stairs that has the meeting ID. You fill that in, hit join, and then you'll be asked for the password.
And the password is there?
It's on the sheet. It's the piano one, remember? Okay. I'm sorry about that. Kids have piano practice. Okay, so the hypotheses for this third experiment was that performance would improve and mental workload would decrease with both maps. Now we're only going to use the MITS and the TrackUp with civilians. That both of those performance would improve and mental workload would decrease with practice. And that the initial differences in performance that we thought we would see in both performance and workload with MITS would decrease over time. So we thought that we'd have initially that TrackUp map would be better, as we'd seen in experiment 2, but that difference between the two would decrease over time. We did a little bit different setup this time. It's a very similar task, so it's the same task as experiment 2, but now the individual trials were shorter. And so whereas previously we've been running trials that were about 10 to 12 minutes in length, primarily because that's the amount of time that we needed to collect enough data with the DRT task to feel confident in that data. But this time we shortened those tasks. It was about 4 minutes for each trial. And people would perform 6 trials, and then they would go away and they would come back either, I'm trying to remember, it was 2 to 4 days later, and they would do a second session, and then they'd go away and they'd come back 2 to 4 days later and they'd do a third session. And that timing was based on prior research in VR in terms of getting a sense of how long it took to build up experience. And of course, anytime you're working in virtual environments, you have to be very careful about, in simulation environments in general, you have to be concerned about simulator sickness. So we couldn't expose the participants to the environment for too long without risking increase in occurrence of the discomfort. So participants used either the MITS or a TrackUp map and performed those 3 sessions with 6 trials each. They did do the DRT detection task along the way, avoided obstacles, and again completed questionnaires. And here we're going to look at the task performance in terms of their time in collisions and the mental workload across those 3 different measures. And what you can see in these very nice graphs, these are exactly the types of graphs you expect to see as learning happens. We can see that the task completion times and the number of collisions decrease. And for the most part, this happens over the first 2 trials. Once you get to trial 3, we basically see very little continued improvement over time. And the differences between the 2 groups become quite a bit smaller over time as well. And so these trials being about 4 minutes in length, keep in mind that you have a training trial that's also about 4 minutes, suggests to us that over a period of about 10 minutes of experience in the virtual environment, people can use either of these, civilians can use either of these 2 maps to perform these tasks at a pretty much equal performance. And also I can show you workload. So you see the workload results. So the hit rate on the top going up is good. The response time going down is good. So you see that we see both of those things. And then the global workload rating from the NASA TLX, you see those decreasing as well. Interestingly, you actually see higher ratings for the track-up map than for the MITS map when it came to global workload assessment. So these were pretty interesting results to us, because it suggested to us that what we've been doing, it took me 25 minutes or so to describe those 3 experiments to you. It took us over 2 years to run them. So we had a lot of time spent thinking that we were not really showing any benefits to this display concept of MITS, and actually developing the impression for a good period of time that it was inferior to more traditional 2D map presentations. But following this experiment, we feel a bit more confident. The other thing you can see here, which I've not talked too much about, is the map switch on the far right of each of those graphs. So what we did in the last trial on the 3rd session was we had people use the opposite map. So this was a between subjects design. So participants used one map throughout the experiment until that final trial, and then they switched. We were wondering if it's harder to switch to MITS from track or harder to switch to track from MITS. And you can see that there are some differences there. We have to be very careful about how we interpret this data, because there's really only 4 minutes of data here. But you can see that there are some effects that switching from one to the other is not the same experience. So it is easier to switch to MITS if you have had some exposure to the environment already. Okay, so the summary of all of this is that the first 2 experiments demonstrate that based on initial exposure, participants may not perform as well using this novel map format, and they may experience higher workload compared with more conventional map formats. But the final experiment showed that with practice, these disadvantages can be reduced or eliminated. So in the long run, what we're trying to understand is how efficacious is MITS as a map concept. We understand now that it may take time to learn it, which we would have to build into any further testing, or that we would have to build into any plans for trying to expand the research program on MITS. And it may actually, we have other results that suggest that there are advantages to MITS in particular tasks such as distance estimation. So if people are, instead of moving through the environment, if you're asking them questions like, how far away is that object relative to that object? Pick the object that's closer to you, or give us an estimate of how far away that object is. We actually see advantages from MITS up until a certain distance. When the objects get too far away and they get squished down in the virtual environment in that representation, then that advantage goes away. And then finally, we've had one really interesting master's thesis that a student did for us, looked at different ways essentially of shaping that dome, or not like the dome, like we could do it as a flat map. We could create a dome. We could use orthographic projections, or equal distance projections, or equal angle projections. So there's all sorts of, from cartography, we can come up with different ways of arranging the environment, of arranging the shape of that mirror, and see how that benefits or aids or disadvantages certain tasks. And one of the interesting things that came out, that I'll finish on, that came out from that experiment, was that we had been using more or less the default orientation configuration of that map that the developers had come up with, because the developers have all sorts of things that they were doing as they were creating the map in terms of how far forward was it projected, how is it bent and stretched, what happens at the corners. All of these software manipulations were taking place. And essentially, one of the conditions of that master's thesis, as the student was comparing these different projections, was sort of the default one that we'd been given by the proponents of the technology, the developer of the SkyMap, and that actually turned out to be the worst of the configurations that we tested. And so what that told us was that there's actually a huge amount of value in exploring the different variations of the map and the impacts on human performance, because the designer's intuition turned out to be pretty much the worst option that we explored. Okay, so thank you very much for listening to this story about these 3 experiments. And if you have any questions about this work or extensions of this work, I'd be really happy to hear your thoughts.
Yeah, thank you very much, Greg. Let me see if there are any questions. So you could unmute yourself if you have a question, or you could type it in the chat, and I'm willing to read it out. But I thought that was a great presentation. Whilst I wait for questions from other participants, I have a couple of questions that I want to ask. So, I mean, great job you're doing. I'm kind of wondering what the results would be when you actually project these onto real AR glasses, and where there are tracking issues, and you actually taking data from the participants, what the results will turn out.
Mm-hmm.
Yeah, but the question I have is, what was the sample size, especially for the large experiment?
The large experiment was 72 participants, so it's 36 civilians and 36 soldiers in that study. So we had certainly adequate power in that experiment. The longitudinal study was only 20 participants. I mean, it's a huge amount of data to collect. And we collected the 20th participant the day that our region was shut down for COVID. So we would like to collect more data on that study, because we do believe that there may be small effects that we have not been able to detect just because of the small sample size.
Okay, so again, whilst I wait for questions, I have lots of questions, right? So I did see that you intended to use a polar heart rate monitor to collect data, but I didn't see any results from that. And one of my research interests is to look at the associations and dissociations between these physiological measures, and why sometimes the results you get are not explanatory. Was it one of the reasons why you didn't report on it?
Yes. So that's really a fantastic question, and my student Holly Vasquez, I'm sure, would be really interested in speaking to you about this. You'll be happy to know that Peter Hancock was her external examiner, and Peter is published extensively on the relationship between different mental workload measures. Essentially, our DRT task proved to be sensitive to differences in mental workload, and sometimes the NASA TLX, but none, to my recollection, across all of the studies, all 3 of Holly's studies, there were no statistically significant differences in heart rate variability, and then, as you know, there's a variety of other measures associated with heart rate. And so that was quite interesting, and I would actually really encourage you. It's funny you mentioned the polar heart rate monitor in particular. Her first attempt to publish this in Human Factors was ultimately rejected because the reviewer basically blamed the lack of statistically significant results on the polar monitor itself. Basically said that we should have used a more sensitive device, which was kind of surprising. But nevertheless, that was the attribution in that reviewer's mind. Actually, it was the acting editor's mind. So I would encourage you to get in touch with Holly. She would, I'm sure, love to talk to you about that particular result herself.
Okay, thank you. Any more questions?
Hey, Joseph, if you don't mind, can I ask a quick question?
Yeah, go ahead.
It's not very technical. Hello, Greg.
Hello.
That was a very interesting presentation. I really enjoyed it. Very different from what I'm used to. So I was really enjoying the entire presentation, the setting, the context. I was just curious. So were all of these experiments when the participant or the user was walking? Is that the operating?
Sure. Yeah. Maybe I didn't give a good the one image that I
That's the
showed.
impression I got, but I just wanted to make sure.
So they are not physically walking. So in the environment, they can turn around. They can walk a few steps, but they're in a small room. And if as they turn, the trying to remember the name of this, the Oculus can tell where they're oriented and adjusts the map over their heads or in front of them as they turn around. But then they move through the little thumb joysticks on the
Okay.
controllers, and so that is how they indicate that they want to translate through the environment.
So the virtual walking that's controlled on the joystick, so the speed of that would obviously impact how well they're able to, recognize and navigate, right? Uh,
Absolutely.
So I was just
Yeah,
curious.
so this has been this has been one of the experimental design variables that we've struggled over quite a bit. Essentially what we did in the studies that you saw was that people were essentially moving at jogging speed. One of our postdoctoral fellows did a study where she essentially put people at bicycle speed, like as if they were riding a bicycle through the environment. Several of us wanted to do studies at walking speed. The reality is that people get bored at walking speed in virtual environments. It takes too long to get anywhere, and it if you're looking at how they perform like at intersections and that sort of thing, they just don't get to enough of them before they start to get sick because of the virtual environment setting.
Okay. So when the speed was increased, you don't see any drawbacks from doing that. I was just wondering, is a
Yes.
driving application of this sort of navigation even too crazy to imagine, given how quickly you have to adapt to it? So,
Yeah, I mean, bear in mind that the research question was about how dismounted soldiers would use this type of technology. The developers, Uncharted Software, they have concept drawings of like depth, like a ship deck. You know, the sorry, I'm trying to think of the word, the control deck of the ship. I'm not sure what the right language is. I apologize. But you know where the people driving the ship are, and sort of they have representations of that. They have done a technology demonstration for an armored vehicle, but it's just the technology is just not sort of keeping up. Like you can't at the speed that the vehicle can move, the computer can't keep up to render the environment. Can't rent, and that was in an augmented reality setting. It just can't render it fast enough. I don't necessarily think that the concept is limited to velocity, right? I think it's just that the computing power is limited to velocity. And in the one experiment that we ran with at the bicycle speed, we did find that errors in judging when they had arrived at a location were quite a bit higher than in other studies. So it seemed that just going faster led them to make poorer judgments of where they were in the environment.
okay. That's interesting. Thank you. That's
Thanks
all
for
I
the
had.
questions.
Nothing technical. Thanks.
Yeah, thank you.
Joseph,
Best. Yes.
Joseph, if I can just interject for a second and just ask.
Okay. Suresh, go ahead.
I don't have a question. I had to, by the way, I'm Sundaresh Sharigam. I'm the head of the School of Industrial Engineering and Management. First of all, I want to thank you for visiting us virtually. Normally, when we do these seminars, we actually bring the speakers in, they stay overnight, we have dinner at a nice place. I'm sorry we can't do that this year.
Thank you for that. I'm sympathetic. We're currently interviewing candidates here, and we have exactly the same problem. We feel like we live in a beautiful city, and we want people to come experience where we are, and we just can't do it. So I appreciate your saying that.
Yeah, and I also want to mention that you seem to be a pro in Zoom. You're able to do multitasking on the fly with your daughter's piano lessons. And
Yeah, aren't we all though these days?
I unfortunately had to take a call in the middle of your presentation that was important, so I didn't listen to the whole thing to be able to ask you a question. But I just wanted to thank you for participating, and thanks Joseph for inviting you. By the way, this is not meant to close off the session. I think there may be more questions, but I just want to button and say thank you, Greg.
Thank you for your invitation, and we do these departmental seminars as well, and it's certainly always a pleasure to have an opportunity to visit someone else and talk about the work that we do.
Yeah, thank you, Sundaresh. Greg, I have another question again, whilst we wait for others to ask. So the last experiment, which of course kind of explained or made whoever the sponsor of your project is know that there's some kind of utility in what you're doing.
Mm-hmm.
I have a question on that. So you did conduct a between subject experiment. Would the results have been different if it had been a within subject design?
Yeah, and so simply we just didn't have like the time to collect to use it within subjects design there. It could very well be that transfer trial does suggest that that the to some extent it's the experience of the environment that matters, and I don't want to say as much or more so, but it definitely matters in addition to the experience with the map. So it's quite possible that just people who gain some experience in the environment and then given a map, like we could potentially do an experiment where we give people at least 10 minutes of experience in the environment before we introduce the map, and that might be enough to attenuate these differences between the displays. So we haven't done that. But your question does give me an opportunity to speak to, so a lot of the research that we have the opportunity to do in Canada, especially engineering research, is through partnerships. So we're very fortunate in Canada at both the provincial and the federal levels to have matching programs for industry dollars. So when companies find a synergy with an academic researcher, they can put up dollars that both the province and the federal government will match to do research. And so essentially what it does is it multiplies the research dollars that are available and allows us to bring in a bunch of students. So for this research, between the military at the federal level and the provincial level, a $50,000 input from the industry partner resulted in $250,000 of research funding that we were able to deploy. And these numbers are always like, our numbers are always smaller than yours, but our costs are much lower than yours too. So the cost of a student here is almost certainly much lower than it is there. So we get a lot out of it. We were able to support 6 graduate students, including a postdoctoral fellow on that funding for several years. And what this always invites the risk of that you're in close with the proponent of the technology, right? And I was really pleased. I've done a lot of these types of research programs. I was so pleased with this partner on how intellectually invested Tom Kapler was in the research. He certainly still is a proponent. He wanted us to find ways of showing, strengths. He really did. But he never tried to sort of bury any weaknesses. He never shied away from the results. And that was really nice. It was nice to come out at the end and be able to say, hey, Tom, this years of telling you that your idea was not quite up to the existing solutions. He hung in through all of that, never suggested we stop doing anything. And then to be able to show him, hey, we actually think that it may be that we were simply testing people too early in their experiences. So that was a huge bonus for us. We're really pleased to have that opportunity to work with the technology developer in that case.
Yeah, I still don't see anyone asking a question. I probably will ask my last question. Yeah, I seem to be asking all the questions, but well, the secondary task that you chose, what informed that choice of that particular secondary task?
Yeah, it's interesting you ask it, and the reason for that is that the student's undergraduate research was in driving. So she was a transportation at Virginia Tech's Transportation Institute, and she had seen the DRT used there. And when she wanted her emphasis in her research was on workload, and she wanted classically in human factors, if you're going to look at workload, you want subjective, physiological, and secondary tasks are the 3 major categories of workload assessment. And excuse me, she wanted to have that secondary task, and she was familiar with the DRT, and so she actually built her own apparatus to do it. And there is a standard, by the way, for that task. If you're not familiar with it, there's I think it's an ISO standard. for that task, which is great. So we had everything that we needed to know to construct the task, and so that was why we chose that one. And based on that experience, I'd say we definitely use it again. It definitely appeared to be more sensitive than physiological measures of workload. So again, if you're interested in that in particular, Holly would be a great person to talk to.
Sure, do that. Thank you.
All right. Well, thank you all very much for attending. I know I've been to many of these myself, and I know when I go to the operations research ones, I really struggle to come up with any questions to ask. But I hope that you got something useful out of it. If you're not in the human factors area, certainly I try to learn from my industrial engineering colleagues when I can, when it's in areas I don't know about. So I really appreciate you taking the time to listen, and I hope you have a great rest of your day.
Yeah, thank you. So thank you very much, Greg, for delivering such an insightful presentation to us. Again, as you said, many of the folks are the human factors guys, but you came across, as far as I'm concerned, clearly for people to even ask questions. So we're so grateful, and we wish you a very good rest of your day. And for participants, just for you to know that this is recorded, and shortly we'll send you the link to be able to view it if you want to. Thank you very much. And
All right. Thank you all.
Thanks again, Greg. Appreciate it.
So long. Let us know if you're ever in Toronto.
we'll do. Okay. Bye-bye.
Bye-bye.